way to actually create this curve. Notice when I put in the board, didn't I draw it this way? I might refer to that as the orientation. There are two different ways that can go. And so I think at this point right here, there would be a tangent vector, a direction vector for that particular curve. Because it's a closed curve, I like to talk about rotating about it in a specific direction. I also might use a word called orientation. I've just shown the orientation of my curve. But at every point like this one, I also think there's a normal vector. Oh, did I just make a mistake? I think I did. You guys watch. At that one point with a normal vector, maybe it went this way. So do you guys see my point? Oh, no pun intended. Every single point on this curve has two distinct normal vectors. One going to, if you want to say it this way, to the outside, one going to the inside. Now, in this chapter, we need to be careful that all my curves, or even surface and free space, have to be orientable. Meaning at every single point on the curve of the surface, there are going to be two distinct normal vectors. Can you guys think of a curve that does not have equality?
That one.
What's that?
That one.
Well, no, this has a quality that at each point it's got two distinct normal vectors. Can you think of a curve or a surface that does not have two distinct?
The one that goes on the inside and outside of the top?
Thank you. We call it the
Four-dimensional thing.
Mobius strip. Have I talked about the Mobius strip in class?
Yes.
Yeah.
So we've drawn it. Good. I'm glad it did because I was going to eventually. And so that's
Say that again. Each point on the curve
Each point of the curve has to have
a
two
tangent,
distinct.
a tangent.
No, don't look at tangents anymore.
Okay.
Just look at the normal vector. I would say that my curve is orientable if at each and every point there are two distinct normal vectors.
I don't get why the Mobius strip doesn't have that quality.
Actually, it would, wouldn't it?
I disagree.
It's one long side.
And so as I'm pulling this out, Linda, can I add to that then? Now I'll say that a surface is orientable if at each point there are two distinct normal vectors.
If you like take a surface, like let's say you take a piece of paper and like you make a sphere out of it,
Yes.
it's only going to have like normal vectors pointing out, not in.
See, I disagree. I can think of the normal vectors pointing in. Therefore, at each point on the surface of the sphere, there are two distinct normal vectors.
But if you just take like a plane and then fold it into a sphere,
Yeah, what about that?
oh wait, with plane, oh that's right, plane.
I think the plane as it is, and as you're moving it to close into the sphere, it's still orientable because at each point there's two distinct normal vectors.
Yeah, because the plane has.
I just maintain that when it comes to this Mobius strip, that's not the case.
Oh, I don't know.
Here's why. Because at this point right here on the top, you can consider normal vector opening upwards. But if I travel along the surface, I haven't changed size. I haven't crossed a boundary, and therefore there's only one side to the surface, and therefore I don't treat those normal vectors distinctively. This is a one-sided surface.
Let's say that you just look at one limited section, right? You bound it.
Yes.
One little part.
Yes.
You put your fingers there. And you're on this side of it. Just looking at that, technically you could have one pointing down and one pointing up. Just because when you continue and you end up on the same side on the other side doesn't mean you now only have one, right?
And I see your point. Maddie's saying this. If I take some scissors and cut here and cut here, I just got a little rectangle. It's orientable. The problem I have is the language that's missing, which I'll add in a minute. Yes?
And this is largely a result of the fact that you're dealing with these closed spaces where
That's true.
basically you've got a separable inside and outside.
That's true. I agree. Do you guys think I can take a piece of paper, just fold it up and somehow make a sphere?
Sure.
Yeah, why not? Why not?
Like
A three-dimensional circle. Yeah, a ball. I think I'll fold a piece of paper, cut it maybe, or hold it here and there, and transform it into a sphere. There's something referred to as topological equivalence, where I can morph one image into another by sliding, pulling, stretching. And so, Maddie, coming back to what your question was, I can't take a little rectangular piece of paper and use those same transformations to convert it to this. Because this required rotating and then connecting. And so I think it's a whole different ballgame when you say, oh, just look at a small piece of it. This is closed now. And as a closed surface, I think it's non-orientable because there's only one side to the surface. And of course, that higher dimensional, four-dimensional object correlated to this was the line bar.
So because it's a
The line bar.
one-sided surface.
It's a one-sided surface. So you guys, can you help me? Can you help me with what the heck that example was last time in class? I really don't Because I had a line integral, I said, remind me next time we'll finish.
It was a IDX plus XTY.
So why, whoops, I just had a nice pen the last time, did I put it in there?
It was a mistake.
It was. So Eric,
YDX plus XTY. C1, R sub naught equals 1 comma 1.
well, actually, just give me those points. It was 1 comma 1 and
1 comma
was it
1,
2, 4?
2 comma 4.
Right, because I had a parabola. So you guys help me with this. Am I labeling things okay? C1, C2, and C3?
Here.
All right, hold it. I had arrows in here, I think. And as I recall, when I did answer the question, what's the evaluation line integral from, or along the curve C1 and C2, is that correct?
Yeah.
So let's check out C3. Let's get back into this. Along C3. To evaluate this line integral, I think I can actually rewrite this just in the typical way I did with Math 3. Because I think if I break up that curve C3 into 2 segments, the first of which is this red one, I think with that red portion of C3, all I'm really doing is treating y as a constant. And so I think a parametric representation of that one piece of the curve that I labeled C3 could be this. Namely that x is equal to, x is, I think it's just itself over the interval from 1 to 2. And I think y is equal to, well, isn't it just positive 1? It's just a constant. Oh, by the way, you guys, since we're here, help me out with this. What's dx? According to this relationship, dx is, well, how about saying itself? But down here, I think dy is equal to 0. Let's slap everything in. I think the value of this line integral, I simply got the integral in which x is ranging from 1 to 2, and let me plug everything in. Another name for y is positive 1. Plus x times, yeah, the y is not changing. And so I think in the end, this amounts to having the integral from 1 to 2 of just simply 1 with respect to x. Oh, you guys, I just goofed. Hold it, this isn't going to work. Actually, it's not all of C3. So allow me to make the last bit of a trip along C3, moving in the vertical direction. Let me not write. This time y is ranging from, I'm sorry, it's slow, 1 to 4. But x is a constant at 2. Let me throw everything in. Life is this easy. I now have a second piece being the integral from, we said 1 to 4, and let me slap everything in. Another name for y is just itself. But y is changing, so it's just itself. But another name for dx is 0. Yeah, because the x values are all constants. Plus my x values, which are all at positive 2, times my change in y. Or shall I say, I've got the addition of the integral from 1 to 4 of 2 with respect to y. Oh shoot, you guys, isn't this a piece of cake? This just simply gives me, instead of 1 plus,
6.
is it 6? Thank you. I agree, which is 7.
They're all 7.
They're all 7s. So this particular line integral is not line, or excuse me, is line independent. Doesn't matter what path I took, I got the same value. Any questions?
So,
Can you give us one that's line dependent?
You said that you wanted it to be line dependent? Yeah, same question.
Well, actually, in practice, it's going to be really beneficial for me to have it line independent, because it's going to allow me to do things. Most of our examples are going to be like that. Here's why.
Wait, use that vocabulary again, independent, dependent.
I said in this example, since all those paths gave me the same evaluation of line integral, I would have said that the evaluation of this line integral is line independent, because it didn't matter what path I took, I got the same value.
Well, we need to clarify it's line independent over those paths since you haven't tried that.
Yeah, over those paths, you're right. Now, I don't want to get into that too heavily, because what's going to happen in the near future is we're going to check for independence. And when we do that, we'll be able to use a whole new version of our fundamental theorem of calculus. This is what I refer to as my fundamental theorem of line integrals. You just give me another day, and I'll dive into it. Matt?
Yeah, so, I can't remember, why are we doing this? Like, what, so, we have line integrals, yay. What are we doing it for? Sorry.
Defense.
Yeah, I know, but Maddie, when I talked about the fence, that was a goofy way of saying this is why we're doing it. Because in practice, we're not really gonna look at it that
Well,
way.
I liked it because it gives me an idea of,
And that's why I said it that way, because I think it's a nice intuitive approach to what these things are all about initially. Yes?
So way back when we first started talking about gradients, we talked about it as like a path of greatest descent, but that only really told us at one point. Could we look at a surface as like a vector field and use line integrals to determine the path of greatest, or?
Yeah, and a lot of times I actually do that just visually. A lot of times. Matthew, I never answered your question. If I have a vector field, and,
That's the symbol for a vector field?
no, I'm sorry, I'm thinking about writing this thing.
Oh.
I'm trying to think of something I can say to clarify this. If I have a vector field and a curve in the vector field, and I want to find out how much work it takes to get through that vector field along that curve, I can think of that as an integral, where it's an integral involving a vector field, call it f bar, which is fucking 2 or 3 variables, times the rate at which tangential vectors are changing. And so remember the curve I had on the board earlier? If I did this on this curve, and I had some vector field flowing in some direction, I could talk about how much work it takes to actually move through that vector field along that curve in 2 space. And I can use these line integrals to evaluate that element. Work is just nothing more than, work is force times distance. And think of the vector field as a force being applied to a particle or an object moving along this curve. And dt bar is really the path of basically I'm traveling on, the distance I'm traveling. Because the dt bar just simply represents these tangent vectors, the unit tangent vectors. So sometimes I might even refer to these as line integrals over vector fields. Since you mentioned it, I'm going to just dive into it then.
So it's the Riemann sum of all those little tiny lines.
Yeah, if you want to think of it that way. It's just that when it comes to the Riemann sum, I will think of the x, y, z courses as functions of some parameter like that. Now, what's really cool about this, again, I'm just trying to address your question, is I can find out the net flow of fluid maybe going in a certain direction around this particular object. I call that circulation. Sometimes I want to know about the net effect or the net result of water maybe flowing out of this particular object. You guys, a lousy picture, don't look at it. Do this instead. I got a net in the ocean, and I'm pulling it along. I can talk about how much material is going through the net. I sometimes refer to that as flux. And notice that's just very related to circulation. It's just as circulation goes along the surface, whereas flux goes out of the surface. And those are the real reasons why I need to talk about identical surfaces.
Explain that one more time.
Yes. Look at this curve. If I want to know the net amount of flow along the curve in the direction of the curve, I sometimes refer to it as circulation. And I sometimes use the word flux to describe the net effect or the net amount of material going outside the curve, going away from the curve. Or if it's a surface, going through the surface away from the center. Whatever center it is. Called the inside.
Okay.
Oh, I guess I can't. I can't do that with this non-zero. Is that helping, Matthew? Because I do think when I came to class, I said, oh, look, funky little stuff about painting the side of the fence was goofy in terms of serious applications.
on that, straight,
The Mobius strip.
sure, how, if you were just trying to write an equation for where on the strip you were, how would they know if you were, like, you can't say inside and outside, how do you know when you're technically in?
And therefore, all I can do is identify the point of the surface. You just can't talk about insides and outsides.
But I mean, there is an inside, right?
See, I disagree, because the inside would have to have a normal vector that's opposite of the normal vector that goes to the outside.
Can't you have a normal vector that's going to hit itself to the other side? If you can say like the normal vector, if extended, would,
If extended, like, through the universe and come back to the other side. That's what you mean.
look at the strip, here, you
Yes.
see the strip thingy?
The thingy.
Yes, exactly. So like, well, I think what she's saying is if I were to take a vector and extend it out from this point right here, it's gonna hit the other side. So isn't that gonna be the inside of it?
No, it bends a little bit. Now it's not gonna hit.
Well, then point us in the direction.
See my point?
Well, if we point the other direction, then it's not gonna go anywhere. Okay, so you can just move this thingy around and make it so it's not gonna hit something and say that, oh, is it just because
I
this
think
is
the
a,
whole hitting it is completely 100% irrelevant of the
To
nation
whether or
that is
not.
one step
Well, I'm trying to
here.
think of a way to define, like, because you know, when you're looking at it, it looks like a circle.
it does look conspicuously like a circle.
My gosh, it looks so different from the circle.
Or like an infinity sign if you go this way.
Do you have a cylinder that's the Mobius, or like that goes on forever? Where the sides of the Mobius would go on? Because then that would hit itself.
That's a good question. You're going indefinitely.
Trying to get any way or.
Going on indefinitely.
All the sides.
That wouldn't be a movie strip anymore because I wouldn't be able to talk about the edges. Because they'd be morphing into each other. I think the surface would be connecting in other directions. And I think that would be the problem with taking the movie strip and just taking these dimensions right here and just increasing to